Section 6: How rising and falling sea levels modify the landscape. Digging deeper. How rising and falling sea levels modify the landscape. People living along or near coastlines and even far inland are in areas with landscapes that were affected by sea level rise. This rise followed the retreat of the Pleistocene ice sheets. Here are some examples. New York City is located on several islands. The channels between these islands, such as the East River, which separates Manhattan from Brooklyn and Queens, are former stream valleys. They were flooded by rising sea level. The Hudson River flows south for 507 kilometers or 315 miles from the Adirondack Mountains of upstate New York. After flowing along the west side of Manhattan Island, it drains into the Atlantic Ocean. The floor of the Hudson River is below sea level for much of its length. This is because the river cuts its valley deeply when sea level was much lower. In fact, the former channel of the Hudson River can be traced far out to sea beyond the present shoreline. The channels of many other rivers can also be traced in such a way. Baltimore, Maryland, and Providence, Rhode Island became important seaports. This is because of their protected harbors. The harbors of both cities are in river valleys that were flooded as sea levels rose. The Mississippi River and its tributaries are often located on flat floodplains flanked by steep bluffs. During the Pleistocene epoch, the Mississippi and its tributaries cut their valleys much deeper than at present. Sea level was much lower at that time. As sea level began to rise, the valleys filled in. Sea level change. Earth's oceans are rising because of climate change. The main cause of this change is the melting of ice sheets and glaciers due to increasing global temperatures. This melting is adding more and more water to the oceans. The more water in the oceans, the higher the level of the sea. According to the U.S. National Oceanic and Atmospheric Administration, or NOAA, the annual loss in mass from the Greenland ice sheet between 2003 and 2013 is in the range of 200 to 300 gigatons per year. This is a lot of water. 1 gigaton is about 264 billion gallons of water. The melting of 365 gigatons of ice would add 1 millimeter to global sea level. As the oceans become warmer, their volume is increasing for the same mass of water. This effect is because of the thermal expansion of seawater. However, the thermal expansion of oceans is not evenly distributed. Figure 2 shows the trends in sea level change from both increases in ocean volume and thermal expansion. Look at the parts of the map that are red. In these places, the oceans are becoming warmer and rising more than those places with temperatures that are not changing as much. If you look at the North Atlantic, you will see that the sea level is rising along the east coast of the United States toward Greenland. The graph shown in Figure 3 shows the incremental changes in global sea level that have occurred since 1980. Modeling the effects of sea level rise. Scientists face many challenges when developing models about sea level change. The scale of their models depends on the questions they are trying to answer. For example, scientists know that the Greenland ice sheet is melting. However, a model that demonstrates this change would have to consider how much of the melting at the surface of the ice sheet is due to changes in precipitation and surface melting. Precipitation adds to the glacier's store of water. Changes in precipitation occur over short time scales. Scientists would also have to consider how much of the loss of the ice sheet was due to changes in glacial discharge. Discharge occurs through iceberg calving, submarine melting, and meltwater runoff. This kind of change is permanent. Only a model that included all of these factors would be able to answer questions on how the Greenland ice sheet might affect sea level in the future. Scientists at NOAA have developed models that illustrate the regional scale impacts of long-term sea level rise. They are important for predicting the impacts of changes along sensitive coastlines. For example, the coast of North Carolina is a fragile system of barrier islands that is at risk from SLR. Rates of SLR along the North Carolina coastline are nearly 3 millimeters per year and rising. These islands protect a vulnerable estuarine ecosystem. Estuaries are bodies of water located where a river meets the sea. Sea level rise changes more than just the elevation of the sea. It also affects ocean circulation as well as the range of tides. Together with winds and storms, these control flooding patterns along coastlines. This has a strong impact on sensitive ecosystems in coastal areas such as the low-lying barrier islands of North Carolina. The model of the barrier island system was created by piecing together different kinds of models. First, geoscientists placed a virtual grid over a map of the area and collected geological data in each square. A three-dimensional map of the coast was made using a laser surveying technique. Next, a mathematical model was developed to describe the changing water depths due to tides and storms. From this, patterns for the wetting and drying of the coastal ecosystem could be predicted. The model was then tested against more field data to see how well the model fits. Differences between observed and predicted outcomes were used to adjust the model. The result is an accurate simulation of inundation patterns in the Barrier Island coastal zone with rising sea level. The model can also be used to help study changes in hurricane storm surge flooding with SLR. Understanding these changes will help with the assessment of impacts on ecological processes. These processes include marsh evolution, productivity of the oyster reef, submergence of aquatic vegetation, and changing shoreline habitats and wildlife. Sea level change over long time scales. Global sea level has risen and fallen in many times in response to the growth and melting of ice sheets in the northern hemisphere. This pattern has dominated the last 2.5 million years. This period is known as the Ice Ages. To construct this long-term record, scientists collected data from many different sources around the world. These include the chemistry of fossilized reefs buried far below the surface and the shells of microscopic marine organisms. Milankovitch cycles may help to explain changes in climate and the advance and retreat of ice over periods of 10,000 to 100,000 years. However, they do not tell the climate story for periods greater than that. The graphs in Figure 6 on the next page show various climate-related variables over the last 800,000 years. Similar patterns among the variables highlight their relationships with climate. Look closely at the gradients of the curves in each graph. Steeper gradients indicate change that happened more quickly than less steep gradients. Important information can also be found in the timing of the different cycles. If one variable changes and a second variable follows at a similar rate shortly thereafter, there is the possibility of a cause and effect relationship. Of course, you will need to gather more information to find out for certain. Changing sea level and human development. One of the most important effects of the changes in sea level was the exposure and flooding of the Bering Strait land bridge shown in Figure 7. The Bering Strait land bridge is simply a submerged connection between Asia and North America. Today, the water depth of the strait averages 30 to 50 meters at its most narrow, and its most narrow width is only 85 kilometers. When sea level is low, it is dry land. When sea level is high, it is underwater. Ancestors of Native Americans may have crossed the land bridge during the last ice advance until about 11,000 years before present. The bridge allowed mammals to migrate between the continents, with lions traveling to North America and horses traveling to Asia. Rising sea level may have been much more important in human history than simply determining the present-day locations of cities. Settled agriculture began in many places about 7,000 years ago. This was about the time sea level rise began to slow down. Before that time, it was rising at a rate that would have made permanent settlement on coastlines impractical. Once sea level became stable, river deltas could form. These provided fertile, well-watered sites for agriculture. Also, river valleys that had once been cut far below present sea level began to fill in with silt. These silted-in valleys created fertile floodplains. The floodplains of the Nile River are one example. One obvious effect of a rising sea level is the submergence of former dry land. Chesapeake Bay is a flooded river valley. Long Island and Cape Cod are ridges of glacial deposits submerged by rising sea level. The English Channel is also a flooded valley. Former river systems can be traced on the seafloor of many places, including the North Sea between Sumatra and Borneo. Inland effects of sea level change. Changes in sea level due to glaciation can have effects far inland because of the way rivers cut their valleys. In steep areas, rivers move fast and erode their beds. In areas of gentler slope, rivers slow down and deposit sediments. A river tends to have gentle slopes near its mouth and a steep slope near its source. The elevation of a river's mouth is called its base level. If sea level drops, the river can now flow onto the former seafloor to a lower base level. Its slope near the mouth becomes steeper and the river begins cutting its valley deeper. The valley deepening migrates upstream until the entire valley is deepened. Remember watching the Nick Point migrate upstream on your stream table? If sea level rises again, the lower part of the valley becomes submerged. It begins to fill with sediment. Once the valley is filled in, the slope is too gentle for the stream to carry sediment, so the stream drops its sediment at the upstream of the filled-in area. The filled-in valley bottom migrates upstream until the entire length of the valley has been filled in. Thus, when sea level changes, coastlines and rivers change too. The changes begin near the new locations of their mouths and migrate upstream. Around the world, the most important reason for sea level change has been the melting and growing of glaciers.